So what we're discussing is Laplace transforms of derivatives. And one of the things we have to establish is a limit. Okay, so we're going to make some assumptions here. We're going to say, suppose we have a function little g, little g of t of exponential order. So suppose g of t is a differentiable function of exponential order, and we have to remember what was that business of exponential order? Well, in a sense, it has to do with a function being dominated by another function, or with the ratio of these two functions being related to something. So saying that is of exponential order is equivalent, that is, it's equivalent to say that the absolute value of g of t is less than or equal to m e to the ct. This, we would say this for some m, for some constant m and some constant c. Now, one thing that we want to bring back from the good old days of, I don't remember, they were good days back in the day, because this is not exactly calculus necessarily. So is how you break that inequality. When you have absolute value, you have an inequality involved in absolute value, you can get rid of the absolute value, but then you have to bring, this really means that there are two inequalities involved. So I'm going to call this number 1 here. Number 1 is equivalent to, and this is where, so whatever function we have in the argument of the absolute value, we will write that function in the middle. To be dramatic here, let's write this in red. That function would be in the middle, g of t, and then that looks like an upper bound still remains as an upper bound. So here m e to the ct, and then the negative of that upper bound appears as a lower bound, minus m e to the ct. So we can either express number 1 as is in compact form involving absolute value, or we can write the negative of that upper bound as a lower bound. We say minus m e to the ct less than or equal to g, and itself g is less than or equal to m e to the ct. So we can have either 1 or number 2. Now, there is no more absolute value here involved once we write number 2. That's precisely the point, trying to get rid of that absolute value. And this is convenient because now I'm going to take limits. Well, I'm going to do something to this expression and then take a limit. And maybe you don't care about this, but I had a sandwich for lunch. And it's a good thing because the limit I'm going to take is called uses the sandwich theorem, right? I know, you probably don't care. It was turkey and Swiss cheese. It was delicious. But so let me write this again. Minus m e to the ct g of t m e to the ct. And I'm going to write every part of this double inequality multiplied by an exponential. In this case, I'm multiplying by e to the minus st. That shouldn't look too foreign. because e to the minus st, well, you'll see, it will work in a minute. But I'm multiplying every term of the double inequality, the upper bound, the lower bound, and the thing in the middle. That's like the turkey and the Swiss cheese in my lunch, right? That thing in the middle, g of t, is also being multiplied by e to the minus st. E to the minus st is a positive function for all values of t. So no risk here on multiplying every term of the double inequality. However, if you're multiplying by something that is negative, that is a risk because it messes up the inequality. It could switch. You would have to be mindful, but no problem here because as a function of time, with t being in the time domain 0 to infinity, e to the minus st is always going to be a positive function when we're assuming s is a positive real number too. So the inequalities are preserved. So we could write the lower bound, let's go ahead and do that, write the lower bound as minus m e to the c minus s, quantity c minus s multiplying by t. Everything else stays the same. G of t times e to the minus st, m e to the, similar here, we can write c minus s, quantity c minus s multiplying t, right? But here we have still double inequality. Now, before, and this is what I want to do next, I cannot wait to take a limit, okay? But I'm going to have to wait, even if I cannot wait. I'm going to have to wait because I'm going to write a note here saying if c minus s is negative, if c minus s is negative, then we're game. If it's not negative, then stop, forget about it. But if it is negative, then take the limit as t goes to infinity. So we're making an assumption. Okay, so let me write that again. So this would be minus m e to the c minus st and we are making the assumption that the argument of this exponential appearing in the lower bound and upper bound, that argument is a negative number multiplied by the independent variable t. Okay, so we make that assumption and then take the limit as t goes to infinity, limit as t goes to infinity, limit as t goes to infinity. So the convenience of taking this limit as t goes to infinity, there's a negative there, yeah, that's kind of handled there, is that we can easily see what the limit of the lower bound and upper bound is. With c minus s being negative and t taking positive values going from 0 to infinity, the limit of e to the quantity c minus s multiplying t, that limit becomes 0. Okay, so that means that in this exercise of taking the limits, this part here is 0, and so is this part. In other words, we have trap, and this therefore being the idea of bread, Swiss cheese, and turkey, and then more bread, right? Trap, like a sandwich, that limit is trapped between 0. I'm sorry, this is just after lunch. This is being recorded. I don't know, and I don't care. So the limit is being trapped between lower bound 0 and upper bound 0, which implies that then the limit of g e to the minus st is therefore 0. So what we're finding here in 2 steps is we find that 0 is less than or equal to limit of g of t e to the minus st, and the limit is taken when t goes to infinity. So that limit is trapped between, greater than or equal to 0, and it's also less than or equal to 0. I guess the key here is the or equal, right? And so this implies, therefore, that the limit of g of t e to the minus st is indeed 0 because of the sandwich theorem from the good old days of calculus 1. Okay, so with that out of the way, we are going to make use of it. We're going to make use of it in just one sec. But so now we want to turn our attention to the Laplace transform of the derivative of a function. Okay, and this e to the minus st appears in the definition of Laplace transform. So we'll come back to this.